Hello everyone and welcome to the second hour of alternating current. In this second hour we are going to talk about series LCR circuit. Then we will talk about the power dissipated in an LCR circuit. Then we will talk about LR circuit, RC circuit and LC circuit. Now here the most important thing is the series LCR circuit. So pay special attention to the first 15 minutes of this video. So without wasting time, let's start learning the series LCR circuit. So when you have got a series LCR circuit, it means that you have got inductor, capacitor and resistor all connected in series. We know that when components are connected in series, same amount of current flows through them. But we are learning alternating current. In the case of alternating current, the current can't be constant, so the current has to keep fluctuating. Let's say this current changes with time as I equals to I naught sine omega t. So the current flowing through each and every component, inductor, capacitor and resistor at any time has to be same. Here I naught is the peak value of the current flowing through each one of them. Now we know that in the case of an inductor, the potential leads the current by a phase of pi by 2. In case of a capacitor, the current leads the potential drop across the capacitor by a phase of pi by 2. And in the case of a resistor, the potential drop across the resistor and the current are in same phase. So the phase difference between current and potential across a resistor is 0. Now if let's say a current I equals to I naught sine omega t flows through all three of them. If I ask you at any given instant of time what will be the potential drop across inductor, so you will say that if the peak current is I naught, then the peak potential drop across the inductor will be equals to the peak current flowing through it times XL, where XL is equals to omega L. Omega is the angular frequency of the current. So you can say that the potential drop across the inductor will have a peak value of I naught XL, and in case of inductor the potential is ahead of the phase of current by a phase of pi by 2. So you will say that the potential drop across inductor at any time t will be I naught XL, the peak value of potential drop across the inductor, sine omega t plus pi by 2. Sir, why you wrote here pi by 2? Because beta, in case of inductor, the phase of potential is ahead of the phase of current by a phase of pi by 2. So if the phase of current at any time t is omega t, then the phase of potential drop across the inductor at any time t has to be omega t plus pi by 2. Similarly, how will you write the potential drop across this capacitor at any time t? You will say that in the case of capacitor, the peak potential drop across the capacitor will be equals to the peak current flowing through it times Xc, where Xc, which is called the capacitive reactance, is 1 by omega c. And we know that in the case of capacitor, the current leads, the potential lags. So if the phase of current flowing through the capacitor at any time t is omega t, then the phase of potential across the capacitor at any time t will be omega t minus pi by 2. So you will say that the potential drop across capacitor at any time t will be I naught Xc, the peak potential drop across the capacitor, sine omega t minus pi by 2, because in case of capacitor, the phase of potential lags behind by a phase of pi by 2 compared to the current. Now let's talk about the potential drop across the resistance at any time t. You will say that if the current flowing through the resistor at any time t is I naught sine omega t, and we know that for the case of resistor, the current and potential are in same phase. So the potential drop across the resistor at any time t will be nothing but I naught into R, the peak potential drop across the resistor, into sine omega t. Now do notice that the phase of potential drop across the resistor and the current are in same phase, omega t. Now if somebody asks you if at any given instant the potential drop across the source is V, the potential drop across the inductor is I naught XL sine omega t plus pi by 2, the potential drop across capacitor is I naught Xc sine omega t minus pi by 2, the potential drop across the resistor is I naught R sine omega t. We can say that the potential drop across the source at any time t equals to potential drop across inductor plus potential drop across capacitor plus potential drop across resistor from KVL. Hence, we can say that the potential drop across the source V has to be equals to I naught XL sine omega t plus pi by 2 plus I naught xc sine omega t minus pi by 2 plus I naught r sine omega t. Now here you can see we have got three functions of potential. The first one represents the potential drop across the inductor, the second one represents the potential drop across the capacitor, and the third one represents the potential drop across the resistor. We need to combine these three equations so as to get a single equation like V effective sine omega t plus delta. What to do? Sir, we will use phasor method. When we add up these three sinusoidal functions using the phasor method, we will take the magnitude of the vector as the amplitude, as the peak value. So for inductor, we will take the magnitude as I naught XL. For capacitor, we will take I naught XC. For resistor, we will take I naught R. And we will take their phase as the direction of the vector. So for inductor, you will take the direction to be omega t plus pi by 2. For capacitor, omega t minus pi by 2. And for resistance, omega t. So if you visualize the phasor diagram to add up these three sinusoidal functions, so think of the phase of current, which is omega t, as the reference. So you will say that the potential drop across the resistor will represent a vector of magnitude I naught R in direction of omega t. The potential drop across the inductor will represent a vector of magnitude I naught XL in direction of omega t plus pi by 2. The potential drop across capacitor will represent a vector of magnitude I naught XC at an angle of omega t minus pi by 2. Now, how to find the resultant of these three? So I can find out the resultant of these three vectors by using this idea. These two are antiparallel. So rather than writing I naught XL and I naught XC, I can visualize a single vector in upward direction, assuming in my mind that XL is greater than XC. So I naught XL is greater than I naught XC. If I assume this, I can remove these two and place a single vector in the upward direction I naught XL minus XC. And we have got this I naught R. Now the resultant of these two will represent the amplitude or the peak value of the resultant potential drop. And the angle made by it with the phase of the current will represent the phase difference between the potential drop net and the phase of current. So let's take it further from here. So I naught R represents the amplitude of the potential drop across the resistance. I naught XL minus XC represents the sum of potential drop across the inductor and capacitor. The resultant of these two will be how much? Sir, it will be somewhere here. That will be under root of I naught R whole square plus I naught times XL minus XC whole square. So from here you can take I naught outside. So you get I naught times under root of R square plus XL minus XC whole square. So the resultant of these two will be I naught times under root of R square plus XL minus XC whole square. And let's say this makes some angle delta. So you will say that the effective potential drop across the three can be written as the resultant value of the potential drop, which is I naught into under root of R square plus XL minus XC whole square sine omega t plus delta. Why? Because the resultant of the potential came out to be at some angle with the phase of current. Now, bachcho, what does this represent? Sir, this represents the peak potential drop. So let's say the peak potential drop is V naught. So V naught equals to I naught into under root of R square plus XL minus XC whole square. And we call this quantity as the impedance. And the value of delta can be found how? We will say that tan delta will be equals to, look into this triangle. The vertical side is I naught times XL minus XC. And the horizontal side is I naught R. And but this angle is delta. Delta represents the phase difference between the resultant potential drop and current. You can say that tan delta will be equals to I naught into XL minus XC upon I naught R. When I naught get cancelled, you get XL minus XC upon R. So using this, you can find out the phase difference between the resultant potential drop and the current. Do understand that if the value of XC would have been more than XL, then the horizontal part in the phase of omega t, you will get I naught R. And if XC will be more than XL, you will get here downwards I naught times XC minus XL. In such a case, you will get the phase of potential somewhere here. So the potential will lag behind the current given that XC is greater than XL. So you need to remember these two things. Now we are going to define a new quantity which is called impedance. And we say that the impedance represented as Z is nothing but under root of R square plus XL minus XC whole square, and you need to remember this. What is the relationship between impedance, peak current and peak potential drop? For a pure resistive circuit, we know that the peak potential drop equals to peak current into resistance. For pure capacitive circuit, we know that the peak potential drop equals to peak current into XC. For pure inductive circuit, the peak potential drop equals to peak current into XL. For an LCR circuit, we got peak potential drop equals to peak current into under root of R square plus XL minus XC whole square. And we call this part as the impedance. So it is kind of the resistance for a series LCR circuit. So you can say that the peak potential drop equals to peak current times the impedance of the LCR circuit. So the impedance comes out to be under root of R square plus XL minus XC whole square, and this is important. Now do understand that for XL greater than XC, you will get the phase of reactance upwards, and this is the phase of potential drop across the resistance. So the potential will lead the current. The phase of potential will lead the phase of current. If बच्चों XC is more than XL, then the same diagram will be I naught R in the direction of phase of current, and you will get I naught times XC minus XL here. So the phase of potential will be somewhere here. In such a case, the current is ahead of the phase of potential by some angle. So do remember that for a series LCR circuit, potential lead the current. Potential lead the current in which one? In pure resistive, in pure capacitive, or in pure inductive? Sir, potential leads the current in pure inductive by a phase of pi by 2. I am not at all saying here the potential will lead the current by a phase of pi by 2. I am saying that the potential will lead the current if XL is greater than XC. You will get a figure something like this. The potential will lead the phase of current, and the current will lead the phase of potential. The current leads potential by a phase of pi by 2 in a pure capacitive circuit. The current leads potential in an LCR circuit if XC is greater than XL. If you get XC greater than XL, then you will get I naught times XC minus XL here and I naught R here. So the net potential drop will have this phase, and the phase of current is ahead of that of the potential. So the current will lead potential if XC is greater than XL, and potential leads current if XL is greater than XC. You need to remember this thing. Now talking more about impedance, we know that the impedance of an LCR circuit is given by under root of R square plus XL minus XC whole square. Here we know that XL is inductive reactance, XC is capacitive reactance. We know that the inductive reactance XL equals to omega L, and the capacitive reactance XC equals to 1 by omega C. Now understand that as omega increases, XL increases. As omega increases, XC decreases. For very low value of omega, for low omega, tell me which one will be higher, XC or XL? So sir, for very low value of omega, XC has to be large. And for very high value of omega, which one has to be large, XL or XC? Sir, XL equals to omega L. So for very large value of omega, XL will be large. Now think of two extreme cases. The first case where the angular frequency is 0. Angular frequency is 0 for a DC circuit. For angular frequency equals to 0, you will say that XL, which is omega L, will be 0. And XC, which is 1 by omega L, will be infinity. So for omega equals to 0, R doesn't change with omega. XL becomes 0. XC becomes infinity. Can you tell me what will be the value of impedance for 0 angular frequency? The impedance comes out to be infinity as XC becomes infinity. Impedance comes out to be infinity. Now think of another extreme case when the angular frequency is very large. If the angular frequency is very large, the current is trying to change very quickly. If I say that the angular frequency is 500 radian per second, It means that 500 by 2 pi cycles get completed per second. So a large angular frequency means more number of cycles completed per second. And what does inductor doesn't like? The change in current. So if you have got large angular frequency, you are trying to change current very quickly and your XL becomes infinity. So for very large angular frequency, think of infinite angular frequency. The value of XL will be infinity. R is independent of omega and XC will be tending to 0 because XC equals to 1 by omega C. As omega becomes infinity, XC becomes 0. So can you tell me what will be the value of impedance of the circuit for very large value of omega? So for very large value of omega tending to infinity, you will say that the XL will tend to infinity and hence the impedance will be infinity. So impedance is infinity both for omega equals to 0 as well as omega equals to infinity. So if you think of the impedance versus omega diagram, for very low omega, as XC becomes infinite, the impedance becomes infinite. For very large omega, as XL becomes infinite, so the impedance becomes infinite. And as the value of omega increases from 0 to infinity, the impedance of the circuit first decreases, reaches a minimum value, and then again becomes maximum. That particular frequency for which the impedance is minimum, that particular frequency is called the resonance frequency. So let's understand the resonance condition. What is said to be the resonance condition for an LCR circuit? We say that under resonance condition, the impedance of the LCR circuit is minimum. And since we know that the peak potential drop across an LCR circuit equals to peak current flowing through it times impedance, or I can write the peak current flowing through a series LCR circuit equals to peak potential drop across it upon the impedance. When the impedance becomes minimum, we say that the current flowing in the LCR circuit becomes maximum. So under the resonance condition, the impedance is minimum and the peak value of current flows in the LCR circuit. So you get the maximum value of current flowing in the circuit when the circuit is under resonance condition. Now for the impedance of this circuit to be minimum, you will say that this part should become 0. Why? Because sir, this R can't be changed. So Z equals to under root of R square plus XL minus XC whole square. Since you have squared XL minus XC, this part can't be negative. Since you have squared XL minus XC, this part can't be negative. Hence the minimum value of this part can be 0. And the minimum value of this part will be 0 when XL minus XC will be 0 or when XL will be equals to XC. For this to happen, you will say that omega L should be equals to 1 by omega C, or omega square should be equals to 1 by LC, or the angular frequency has to be 1 by root LC. So when the angular frequency of the series LCR circuit is 1 by root LC, then XL becomes equals to XC and this whole part becomes 0 and the impedance comes out to be minimum, and this minimum value of impedance is nothing but R. Under root of R square is R. So we say that for resonance condition, the angular frequency can be found. Let's say this angular frequency is omega C. When you have got the resonance frequency for which the impedance is minimum, the current flowing in the series LCR circuit is maximum, you will say that XL has to be equals to XC. XL equals to XC means that omega L equals to 1 by omega C, or you will say that omega square equals to 1 by LC. Once you know that the resonance frequency whole square equals to 1 by LC, so the resonance frequency has to be 1 by root LC, and you have to remember this. So the impedance of a series LCR circuit is under root of R square plus XL minus XC whole square, and the resonance frequency for which the impedance comes out to be minimum is 1 by root LC. If we look at the graph of impedance versus the omega, as I have already said, for very low omega, XC becomes infinite, so the impedance is infinite. For very high omega, XL becomes infinite, so the impedance is again infinite. So as the omega changes from 0 to very large value, the impedance changes from infinity to a minimum value and then again to infinity. Now, if we think of the graph looks something like this. and the value of Z is minimum equals to R when the frequency is equals to the resonance frequency, where resonance frequency is 1 by root LC. At resonance frequency, XL becomes equals to XC. Do understand that for any frequency less than the resonance frequency, for any frequency less than the resonance frequency, as the frequency decreases, XC increases and XL decreases. So for any frequency less than the resonance frequency, XC will be more than XL. As XC will be more than XL, the potential will lag and the current will lead in the phase. For any frequency more than resonance frequency, we know that XL equals to omega L. So as omega increases, XL increases. XC equals to 1 by omega C. As the omega increases, XC decreases. At frequency equals to omega C, both of them are equal. So for any frequency greater than omega C, you will say that XL will be greater than XC. So the inductor's tendency will lead, and hence you will say that the current will lag in phase compared to the potential. Now keep this diagram in mind and let's talk more about the resonance condition. Now under the resonance condition, if we have got this LCR circuit, we know that the impedance of circuit is minimum as XC equals to XL. So the impedance equals to under root of R square plus XL minus XC whole square. Yes sir. The peak current equals to the peak potential drop divided by impedance. Yes sir. If you think of the graph of the current variation with the angular frequency, you will say that for very low angular frequency, the impedance is infinite and the peak current has to be 0. For very large value of angular frequency, again the impedance is infinite and the peak current has to be 0. We know that the peak current flowing through the circuit will be maximum when XL will be equals to XC. They will cancel out each other, the impedance will be minimum and the peak current flowing will be maximum. So the graph goes something like this. So notice that for very low angular frequency, the peak current flowing through the LCR circuit will be 0. For very large frequency, the peak current flowing through the LCR circuit will be 0. And there is a particular frequency for which the peak current flowing through the LCR circuit will be maximum. And this will be when the circuit will be under resonance condition. And we know that for resonance condition, since XL and XC cancel out each other, the impedance is equals to R. So the peak current when the circuit is under resonance condition comes out to be the peak potential drop divided by R, because the impedance becomes equals to resistance. We need to know more things about the resonance condition. We say that the angular frequency for resonance to happen is nothing but 1 by root LC. Yes sir, we have learned this already. When the system is under resonance condition, you need to remember these things. The first thing, XL equals to XC. Sir, we have already marked up. Second thing, the impedance of the circuit equals to resistance, because XL and XC cancel out each other. Yes sir. And the last point is important point. The third point is when the system is under resonance condition, the current is in the same phase as potential. Think of the phasor diagram we have drawn. We have drawn here, this is the phase of current omega t. This vector represents the potential drop across the resistance I naught R. This vector represents the potential drop across the inductor. This vector represents the potential drop across the capacitor. If XC becomes equals to XL, that the system is under resonance condition, these two vectors will cancel out each other. So the resultant potential drop will be in the same direction as the phase of current. So you will say that the current and the potential drop will be in same phase. So when the system is under resonance condition, the impedance is minimum, the current flowing through the circuit is maximum, the value of impedance of circuit is R, and we say that the current and the potential drop across the circuit are in same phase. Now, if you haven't understood anything till now, beta, please go to the very beginning. Start revising, because this series LCR circuit is the most important thing, and if you get this from here, everything is easy. I know this thing appeared to be very tough when done for the first time. Do it thrice and believe me, this series LCR circuit will be done and dusted. So without wasting time, now let's talk about power. Remember how I said that everywhere I use for the whole track of current electricity, power equals to IV. power equals to I square R or power equals to V square by R works only for the case of resistance. So we will say that, let's say the current in a circuit is given by I naught sine omega t, and the potential drop across the circuit is given by V naught sine omega t plus phi. So you will say that at any instant of time, the current flowing through the circuit is given by I naught sine omega t. And at any given instant of time, the potential drop across the circuit is V naught sine omega t plus phi. Notice here I have written that the phase of potential is phi ahead that of current, right? If I have said that the phase of potential is ahead of current, I am thinking in my mind that XL is greater than XC, because when inductive reactance is more than capacitive reactance, then only the potential leads the phase. Now, if you need to find the power dissipated in the circuit at any instant, you will say that the power dissipated is simply IV, where I at any instant of time is I naught sine omega t, and the potential drop across the circuit at any instant of time is V naught sine omega t plus phi. Substitute them. So what you get here is I naught V naught sine omega t into sine omega t plus phi. Now, using sine of A plus B to be sine A cos B plus cos A sine B, in place of this sine omega t plus phi, you can write sine omega t cos phi plus cos omega t sine phi. So you will get that I naught V naught sine omega t as it is. In place of sine omega t plus phi, I have written sine omega t cos phi plus cos omega t sine phi. When I multiply this sine omega t and split it into two terms, what I get is that I naught V naught, this sine omega t multiplied with the sine omega t, you get sine square omega t into cos phi. And here you have got sine omega t, here you have got cos omega t sine phi, so you get sine omega t cos omega t sine phi. Now, if you want to think about the average power dissipated, you will take the average value of everything. Now, what is changing here with time? Sir, in the first term, sine square omega t changes with time, and in the second term, sine omega t cos omega t changes with time. So if you are trying to find the average value, you need to know what is the average value of sine square omega t over one complete cycle. So sir, the average value of sine square omega t over one complete cycle is half. What is the average value of sine omega t into cos omega t over one complete cycle? 0. So on finding out the average power dissipated, you will write it as I naught into V naught because they are constant. The average value of sine square omega t will be half into cos phi. Phi doesn't change with time, right? Now, for the second term, the average value becomes 0 as the average value of sine omega t into cos omega t over one complete cycle is 0. So you will say that the average power dissipated is nothing but I naught into V naught into half into cos phi. Now, what is I naught? The peak current flowing through the circuit. What is V naught? The peak potential drop across the circuit. You know that for sinusoidal function, the IRMS equals to the peak value of current upon root 2, and the VRMS equals to the peak value of potential drop upon root 2. So rather than thinking of this half as half, think of it as I naught into V naught into 1 by root 2 into 1 by root 2 multiplied by cos phi. And then you can write this I naught by root 2 as IRMS and this V naught by root 2 as VRMS. So you will say that the average power dissipated equals to I naught by root 2 into V naught by root 2 into cos phi. This root 2 in denominator when multiply gives you half. And I naught by root 2 is IRMS. V naught by root 2 is VRMS. So you will say that the average power dissipated in the circuit is nothing but IRMS into VRMS into cos phi. Sir, what is phi? Phi is the phase difference between the phase of potential and the phase of current. Now we have got a special term for this cos phi. We say that this quantity cos phi is called the power factor. Once more, this quantity cos phi is called the power factor. Once more, this quantity cos phi is called the power factor. So if the phase difference between the phase of current and potential is 30 degree, they might ask you what is the power factor. So you will say that the power factor has to be cos 30 degree, and cos 30 degree will be root 3 by 2. You should be able to answer these type of simple questions. So let's talk more about power before moving on. Now let's say you have got this impedance triangle. So what is this impedance triangle? Rather than drawing the potential every time, we know that the I part, the current part is same in all three. So we do not write current every time. We say that this represents the resistance. The vertical component is XL minus XC. Place it here. and the resultant of this R and XL minus XC, the resultant of resistance and reactance XL minus XC gives you the impedance, and this is called the impedance triangle. Now notice that the angle you get between the resistance, because resistance represents the direction of phase of current and impedance represents the direction of phase of potential. So the angle between impedance and resistance is your phase difference between current and potential. Once more, the angle between resistance and impedance on an impedance diagram gives you the phase difference between current and potential drop. Our mission is to know what is power factor. Looking at this impedance diagram, we will say that the power factor, which is cos phi, is nothing but R upon Z. So remember that cos phi is R by Z. We have just learned that the average power dissipated is given by Vrms into Irms into cos phi. So in place of cos phi, you can substitute R by Z. So you will say that the average power dissipated in a circuit is nothing but Vrms into Irms into cos phi, and cos phi equals to resistance upon the impedance. We have even learned that the peak current flowing in the circuit equals to peak potential drop upon the impedance. Dividing both the side with root 2, you can write this quantity to be Irms and this quantity to be Vrms. So Irms equals to Vrms upon impedance. Irms equals to Vrms upon impedance. So rather than writing Vrms, Irms into R by Z, in place of Vrms by Z, you can write Irms. So what you get is Irms into Irms into R. So the average power dissipated is nothing but Irms whole square into R. Remember that the average power dissipated in an LCR circuit equals to Irms whole square into R. When I solve a question personally, I do not use that the average power dissipated is Vrms into Irms into cos phi, where cos phi is R by Z, resistance upon impedance. What I use it, I find the RMS value of current in the circuit. I look at the resistance in the series LCR circuit and I say that the average power dissipated in the circuit is nothing but Irms whole square into R. I told you guys in the last hour that in next hour I will explain what is the significance of Irms. Beta, looking at this, the average power dissipated in an LCR circuit is Irms whole square into R. What is Irms? I peak by root 2 for sinusoidal functions. Understand that Irms is that one constant current that can be assumed to be flowing in the circuit so that the power dissipated is equivalent to the actual value. Once more, Irms is one constant current that can be assumed to be flowing in the circuit so that the power dissipated is equivalent to actual value. Once more, Irms is one constant current that can be assumed to be flowing in the circuit so that the power dissipated is equivalent to the actual value. What is the meaning of it? Let's say in a series LCR circuit, the current flowing is given by 20 sine omega t. You will say that the peak value of this current is 20 ampere. But you know that this current keeps on fluctuating with time from 0, 20, 0, minus 20, 0, 20, 0, minus 20. Which constant current can be assumed to be flowing in the circuit so that the power dissipated by the circuit will be same as the actual value? That constant current is called Irms. So rather than thinking that a fluctuating current is flowing, think that a constant current of 20 by root 2 is flowing in the circuit, or a constant current of 10 root 2 is flowing in the circuit. This constant current will dissipate the same value of power as a 20 ampere of sinusoidal AC supply. So Irms is that one constant current that can be assumed to be flowing in the circuit so that the power dissipated is equivalent to the actual value. Now let's remember the basic definition as well. The average power dissipated in an LCR circuit is nothing but Vrms, Irms, cos phi, and all these are variation in which you can write the average power dissipated. Now here, since we are treating the current and potential drop as vectors, one more concept has creeped in here from vectors. If we look at the current and potential and the phase difference between them, we say that we get power loss due to the component of current in the direction of potential. Don't bug me after this. How are you taking component of current? Current is a scalar quantity. I know that. But this is a concept. What is phasor method? A method to find out the resultant quickly, right? So this is a short trick. So we say that the component of current in the direction of potential, I cos phi, is the one responsible for showing us power loss. That's why the power loss comes out to be Vrms Irms cos phi. And we can take one more component of this current, and that will be I sin phi. Due to this component, there is no power loss. Hence, we have defined a term called wattless current. There is one component of this current which is I cos phi that creates the power loss. Vrms Irms cos phi, Vrms Irms cos phi. And there is one more component of this current because of which we do not get any power loss. Hence, this current is called the wattless current. So you will say that Irms sin phi represents the wattless current. It is kind of the component of the current perpendicular to the phase of the potential. Sir, you can't take components of a scalar. I know that. But this is a terminology which is used by electrical engineers, so you should know it. So if let's say you have got a current of RMS value 20 ampere and you have got some potential drop in your LCR circuit, and here the phase difference between current and potential drop comes out to be 30 degree. You will say that the wattless current will be nothing but Irms sin phi. So 20 into sin 30, which is 1 by 2, that will be 10 ampere. So this is a concept you should know. So now let's move on to some important points that you should know about power. First, for pure capacitive circuit and for pure inductive circuit. In case of pure capacitive circuit, we know that the current leads the potential by a phase of pi by 2. In pure inductive circuit, the current lags behind the potential by a phase of pi by 2. So for pure capacitive circuit and pure inductive circuit, the phase difference between current and potential is pi by 2. Yes. So what will be the power factor for a pure capacitive and pure inductive circuit? So the power factor for a pure capacitive and pure inductive circuit will be cos phi, and cos 90 cos pi by 2 is 0. So the power factor, remember it, for a pure capacitive circuit and pure inductive circuit is 0. So on an average, there is no power loss in a pure capacitive circuit and in a pure inductive circuit. Once more, we know that the average power dissipated is Vrms Irms cos phi. For pure capacitive circuit and pure inductive circuit, since the phase difference between the current and potential drop comes out to be pi by 2, cos pi by 2, which is the power factor, becomes 0. Hence the average power dissipated in a pure inductive circuit and pure capacitive circuit is 0. Also remember that I said that the average power loss is Irms whole square into R. So on an average, the power is dissipated only by resistor, not by capacitor, not by inductor. So now second thing, for pure resistive circuit or for LCR circuit under resonance. For pure resistive circuit, when you do not have capacitor or inductor, or for a series LCR circuit under resonance, when the inductive reactance cancels out the capacitive reactance. For these two cases, the current and the potential drop are in same phase. As the current and potential drop are in same phase, the value of phi becomes 0. And the power factor, which is cos phi, will be cos 0, and the power factor will be 1. So remember that for pure resistive circuit and series LCR circuit under resonance condition, the current and potential drop are in same phase. So the phase difference between the current and potential drop becomes 0. So the power factor, which is cos phi, becomes cos 0, which is 1. So remember that the power factor becomes 1. So now let's do a question based on power. When the voltage of source 200 root 2 sine omega t plus 15 degree is applied to an AC circuit, the current in the circuit is found to be I equals to 2 sine omega t plus pi by 4. The average power consumed in the circuit is. First of all, tell me, in this particular circuit, who leads? The phase of potential drop or the phase of current? So you will say that the phase of potential drop is omega t plus 15 degree. while the phase of current is omega t plus pi by 4. Pi by 4 is 1/4 of 180, that is 45 degree. So you get omega t plus 45 degree. As the current leads the potential by an angle of 30 degree, I can say that which thing is more, XL is more or XC is more? Sir, in case of XL greater than XC, current lags, potential leads. In case of XC greater than XL, current leads, potential lag. Since here current leads by a phase of 30 degree, we will say that XC has to be greater than XL. Now our mission is to find the average power loss, right? If the peak value of potential drop is 200 root 2, the RMS value will be 200 root 2 by root 2. If the peak current in the circuit is 2, then the RMS value of current is 2 by root 2, which is root 2. So you will say that the average power dissipated is VRMS, IRMS, cos phi. VRMS will be nothing but 200 root 2 by root 2. IRMS will be 2 by root 2, and cos phi will be cos of the phase difference between them, that will be 30 degree. So you will simply get 200 root 2, the peak potential drop, by root 2. This becomes your VRMS. The peak current is 2 by root 2. This becomes your IRMS into cos 30. We know that beta cos 30 is root 3 by 2. And this root 2 get cancelled. So you get 200 into here 2, here root 2. You get a root 2 into root 3 by 2. You can cancel this out, and here you will get 100. So you will get 100 into root 2 into root 3. That becomes 100 root 6 watt. This is how easy the questions are. Now let's talk about the case of LR circuit. So sir, if you are saying LR circuit, it means that there is no capacitor in the circuit, right? Now let's think of LR circuit in series. If you have got series LR circuit and let's say current I naught sine omega t flows through it, we will say that the potential drop across the inductor will lead the current by a phase of pi by 2. So the potential drop across the inductor at any time t will be peak current into XL into sine omega t plus pi by 2. The potential drop across the resistance will be nothing but the peak current into resistance into sine omega t. Now you will say that the net potential drop in the line can be found by adding these two up using the phasor method. If you think of the phasor and think of the phase of the current as your reference phase, you will say that I naught R is in the same direction as omega t. I naught XL is ahead of omega t by an angle of pi by 2. So here you get I naught R, here you get I naught XL. So the resultant comes out somewhere to be here. And let's say this is at some angle delta. How to find the value of delta? Very easy. You will say that tan delta has to be equals to I naught XL by I naught R. So tan delta will be XL by R. And if you need to find the impedance of this circuit, so you will say that the impedance equals to under root of R square plus XL square. As there is no capacitance, remove the term of XC. So we will say that the peak potential drop is nothing but the peak current into under root of R square plus XL square, and the impedance of the circuit is under root of R square plus XL square, that is omega square L square, and tan delta, tan of the phase difference between current and potential, will be given by XL upon R. Now once you know all these things, you are equipped to solve question based on LR circuit. Do understand that in case of LR circuit, the potential leads the current because we found the phase of potential to be ahead of that of the phase of the current. Let's do some question based on LR circuit, and from here questions come very often. This is important. So the question goes like, a 9 by 100 pi Henry inductor and a 12 ohm resistance are connected in series to 225 volt 50 Hz AC source. Calculate the current in the circuit and the phase angle between the current and the source voltage. So you have got one inductor of 9 by 100 pi Henry and a resistor of 12 ohm that are connected in series. Your mission is to find current in the circuit and the phase difference between the current and voltage. So how to do? It's very easy. Now beta, you will say that the XL has to be equals to omega L. The source has got a frequency of 50 Hz, not angular frequency. We know that omega equals to 2 pi f. So the angular frequency will be 2 pi into 50 and XL equals to omega L. So that will be 2 pi into 50 into its inductance, which is 9 by 100 pi. So you get omega L. In place of omega, write 2 pi into 50, and in place of L, write 9 by 100 pi. Once you do this, you can see this pi, this 2 into 50, and this 100 get cancelled. So your XL simply comes out to be 9 ohm. Now once you know that XL, the inductive reactance, is 9 ohm, you can find out the impedance of the circuit. You will say that the impedance of an LR circuit is nothing but R square plus XL square. Resistance is given as 12 ohm. We have got that inductive reactance is 9 ohm. So we will say that the impedance of the circuit is under root of R square plus XL square, that is under root of 12 square plus 9 square. Under root of 12 square plus 9 square gives you 15. Do it. Under root of 144 plus 81, this becomes under root of 225, that comes out to be 15. Once you know that the impedance of the circuit is 15 ohm, what will be the value of IRMS? The potential given here is the RMS potential. This 225 volt, the potential of the source, is not the peak potential. This is the VRMS. The V peak will be root 2 times this VRMS. So the peak potential of the source will be 225 into root 2. Our mission is to find the current in the circuit. When they just mention the current in the circuit, they are interested in the effective current. That one constant current that should flow to show the same power loss. So do understand, when they are talking about just current, they do not say peak anything. They are talking about the RMS current. So we know that IRMS equals to VRMS by Z. VRMS is 225, Z is 15. So we will say that IRMS is nothing but VRMS by Z. V is given as 225 and Z is 15. So you get 225 by 15, that is nothing but 15 ampere. The second part of question is, what is the phase angle between the current and the source voltage? So think of the phase of the current, let's say omega t. And now think of the impedance triangle. So this impedance triangle do not have any XC. So there is resistance of 12 ohm and there is inductive reactance of 9 ohm. So the resultant comes out to be somewhere here. You will say that tan phi, or if we take the phase difference as phi, tan phi equals to 9 by 12, or phi will be equals to tan inverse 9 by 12, that is tan inverse 3 by 4. So the phase difference between the current and the potential drop will be tan inverse XL by R. In place of XL, substitute 9, in place of R substitute 12, so you get tan inverse 9 by 12, that is tan inverse 3 by 4, and we know that tan inverse 3 by 4, the 3 4 5 triangle, is nothing but the triangle in which the angle opposite to 3 is 37 degree. So you will say that the phase difference comes out to be 37 degree, and since this circuit has got no capacitance, only inductor and resistance, we know that the potential will lead in the phase by an angle of 37 degree over the current. This is the phase of current and the phase of potential comes out to be somewhere here. So you will say that the phase of potential leads the phase of current by an angle of 37 degree. So the current will lag the applied voltage by an angle of 37 degree, or the potential will lead ahead of the current by an angle of 37 degree. So the example I am picking up next is very important. When an inductor coil is connected to an ideal battery of EMF 10 volt. I told you guys in the lecture on EMI, every time they say a coil, always think of a coil to be made up of an inductor plus a resistor. So the question goes like, when an inductor coil is connected to an ideal battery of EMF 10 volt, a constant current of 2.5 ampere flows. So think of an inductor coil, which is nothing but an inductor plus a resistor. And this is connected to a 10 volt battery, and they are saying that a constant current of 2.5 ampere flows. If they have mentioned that a constant current flows, it means that they are talking about steady state. Under steady state, the current becomes constant, di by dt becomes 0, so the potential drop across the inductor becomes 0, so we replace the inductor with a wire. And we know that the constant current in the circuit will be nothing but the potential drop upon the resistance. So this 2.5 equals to the potential drop of the DC supply upon the resistance. So the resistance comes out to be 10 upon 2.5, that comes out to be 4 ohm. So by this much of data, we can say that the resistance of this inductor coil has to be 4 ohm. Now let's see ahead. When the same inductor coil is connected to an AC source of 10 volt 50 hertz, then the current is 2 ampere. Find out the inductance of the coil. So you will say that, sir, when the coil is connected to DC source, the final current is decided by the resistance of the coil, as the final current is nothing but the applied potential drop by the DC source upon the resistance. So we can say that the resistance has to be nothing but the applied potential drop by the DC source 10 volt divided by the current flowing 2.5, and that comes out to be 4 ohm. So the resistance of this inductor coil is now known. The resistance has to be 4 ohm. Our mission is to find the inductance of the coil. They have given me one more data. When this same inductor coil, which is nothing but an inductor plus a resistance, is connected to an AC supply of 10 volt 50 hertz, then the current flowing is 2 amperes. Bachon, tell me, if they say that 2 ampere of current flows, this is IRMS or I peak? This is IRMS. The peak value will be root 2 times 2 root 2. If they say that the supply potential drop is 10 volt, this is VRMS or V peak. This is beta VRMS given. The V peak will be 10 root 2. Now you know that for such a case of AC, the IRMS will be equals to VRMS by Z, where Z is the impedance equals to under root of R square plus XL square. So let's use it. You will say that when the coil is connected to an AC source, the final current is decided by the impedance of the coil. I'm not saying inductance of the coil. I'm not saying resistance of the coil. I'm not saying reactance of the coil. I'm saying impedance of the coil. So you will say that IRMS will be equals to VRMS upon Z, or the impedance equals to VRMS upon IRMS. The VRMS is given as 10 volt. The IRMS is given by 2 amperes. This means that the Z is 10 by 2, which is 5 ohm. Now you know that Z equals to under root of R square plus XL square. We know Z, we know R, we can find out XL. So substituting, we know that Z equals to under root of R square plus XL square. So 5 equals to under root of 4 square plus something square. So you know that this something is 3. So XL comes out to be equals to 3. Once you know that XL is 3, you can find out inductance. How? We know that XL is omega L. The frequency is 50 hertz. So the omega will be 2 pi f. So that will be 2 pi times 50. So you will say that XL can be written as omega L. So omega L, which is equals to 2 pi f into L, comes out to be equals to 3. Substituting the value of frequency here as 50 hertz, you will get that the 2 pi into 50 into L comes out to be 3. So the inductance comes out to be 3 upon 100 pi Henry. Easy. Now this question is important question. You should be able to answer this. This is one of the FAQs, frequently asked out question from AC in competitive examination. So now we have talked about LRC circuit. We have talked about LR circuit. Now we will remove the inductor and talk about RC circuit. What is an RC circuit? In RC circuit, we have got capacitor and resistor connected in series. There is no inductor. When they are connected in series, the same current will flow through them. We can say that the potential drop across resistor has to be equals to I naught into R sin omega t. The peak value of potential drop across the resistor has to be equals to the peak current flowing through it times the resistance, and the phase of potential drop across the resistance will be same as the phase of current. If we think of the potential drop across the capacitor, it will be equals to I naught XC into sin omega t minus pi by 2. In case of capacitor, the potential lags by a phase of pi by 2, the current leads. So you will get I naught XC sin omega t minus pi by 2. If you think of the impedance triangle, to add up these two using phasor, you can think of the reference direction of the phase of current. I naught R will be the potential drop in the same direction. I naught XC will lag behind by an angle of 90 degree, and you will get the resultant somewhere here. You will say that the value of this resultant, the V peak, will be equals to I naught into under root of R square plus XC square. Now, bachon, we know that here in the case of RC circuit, the phase of potential lags behind that of the phase of current by some angle delta. If you need to get the impedance, you will say that the impedance will be equals to under root of r square plus xc square, and in place of xc you can write 1 by omega c, so you will get under root of r square plus 1 by omega c square. And tan delta will be equals to I naught xc by I naught r, so that becomes xc by r. Do remember that in the case of RC circuit, the potential lags behind the current by a phase angle delta. In case of RC circuit, the current leads, the potential lags. Now let's see a question based on this. In an RC series circuit, the RMS voltage of the source is 200 volt. So the RMS voltage of the source is 200 volt and its frequency is 50 hertz. If resistance is 100 ohm and capacitance is 100 by pi microfarad. This is microfarad. 100 by pi microfarad. Microfarad means 100 by pi into 10 raised to the power of minus 6 farad. We need to find impedance of the circuit, that will be under root of r square plus x square. Power factor is cos phi, where phi is the angle between the resultant potential and current. We need to find the power factor and we need to find the current in the circuit. So first of all, let's start by finding out the value of xc, because we already know what is r. We know that xc equals to 1 by omega c and omega equals to 2 pi f, where the frequency of the source is 50 hertz. So you will say that xc equals to 1 by omega c. So 1 by omega, which is 2 pi into 50 into c. C is given as 100 by pi into 10 raised to the power of minus 6. And this 10 raised to the power of minus 6 has been moved from denominator into the numerator. So that becomes 10 raised to the power of 6. So you get 10 raised to the power of 6 upon 100 pi into 2 pi into 50. So you can see its pi get cancelled. This 2 into 50 becomes 100. There is one more 100. So in denominator you get 10 raised to the power of 4. So you are left with 10 raised to the power of 6 upon 10 raised to the power of 4. That gives you 100 ohm. So xc is 100 ohm. Resistance is also given as 100 ohm. So you will say that the impedance of the circuit, which is under root of r square plus x square, will be under root of 100 square plus 100 square. Under root of 100 square plus 100 square gives you 100 root 2. Once you know the impedance, you know what is r, you know what is xc, you know that the impedance comes out to be 100 root 2. Since r and xc both are equal, this angle right here has to be 45 degree. So the power factor angle has to be 45 degree. Or you can say that tan phi has to be equals to xc by r. Since both of them are equal, 100 by 100 becomes 1. So tan phi equals to 1. So phi has to be equals to 45 degree. The next part, what is the power factor? So power factor is nothing but cos phi. Cos of the phase difference between the phase of potential and the phase of current. So you will say that power factor, which is cos phi, will be equals to cos of 45 degree, and cos of 45 degree we all know is 1 by root 2. Now bacho, next part, what will be the current in the circuit? When they just say current, they are asking about peak current or RMS current. They are asking about RMS current. Just like we say that the peak current equals to peak potential drop upon the impedance. The RMS current in the circuit is RMS potential drop upon the impedance. The RMS potential drop is 200 volt and the impedance is given to you as 100 root 2. So the IRMS will be equals to VRMS by Z, and VRMS is 200. So you get 200 upon 100 root 2 and 200 upon 100 root 2. The 0 get cancelled. You get 2 by root 2, that is root 2. So the IRMS will be nothing but VRMS by Z, that will be equals to 200 by 100 root 2, that comes out to be root 2 ampere. Easy? Let's move on. Now we will talk about LC circuit. So in LR we removed capacitor, in RC we removed inductor, in LC circuit we have removed resistance. So if you have got this series LC circuit connected to a power source, the first thing you should understand that this circuit has got no resistance. So there will be no power dissipation on an average, because the power dissipation is given by IRMS whole square into R. So in an LC circuit, you won't get any power dissipation on an average. The same thing I will do. I will say that the potential drop across the inductor will lead the current by a phase of pi by 2. So I will get I naught XL sin omega t plus pi by 2. The potential drop across the capacitor will lag by a phase of pi by 2, and the potential drop across the capacitor at any time t will be written by I naught XC sin omega t minus pi by 2. To find the net potential drop, you will add them up using the phasor method. So think of the phase of the current. The potential drop across the inductor will lead by a phase of pi by 2. The potential drop across capacitor will lag by a phase of pi by 2, and this is how you will get them. Now think of two cases. Case 1, when XL is greater than XC. For XL greater than XC, you will get the resultant upwards, I naught XL minus XC, and you have got this phase of current. So you will say that the potential drop will lead the phase of current by an angle of pi by 2, given that XL is greater than XC. If XC comes out to be more than XL, for XC to be more than XL, the frequency of the source has to be less than the resonance frequency. Think over it. Now, for XC greater than XL, you will get the net resultant downward. So you will say this is the phase of current omega t, and the net potential drop is pointing downward. So you will say that the potential lags behind the current by a phase of pi by 2. In both the cases, whether XL is greater than XC or XC is greater than XL, in both the cases you are getting a phase difference of pi by 2. So the power factor will be cos pi by 2, cos 90. The power factor will be 0. Understand that the impedance of the circuit will be nothing but mod of XL minus XC. So why you have placed mod? Beta, if XL is greater than XC, still you get a positive answer. If XC is greater than XL, still you get a positive answer. You shouldn't report the impedance as negative. Even for this circuit, you will say that the peak current in the circuit will be equals to the peak potential drop upon the impedance, where impedance will be nothing but the magnitude of the difference in inductive reactance and capacitive reactance as the R becomes 0. Understand that the current leads potential by a phase of pi by 2 if XC is greater than XL, and the potential leads current by a phase of pi by 2 if XL is greater than XC. So these are the two conditions you should know. Now let's practice out 3 questions based on LCR circuit before I say you tata bye bye for this hour. So these 3 questions are nothing but a single question. In all the 3 questions, I will use the same diagram, but it's a big question, so I have divided it into 3 parts. So in even the next 2 slides, I'm going to discuss the same question. So the question goes like, in the circuit shown in the figure, find the reactance of the circuit. Find the reactance of the circuit. So what is reactance? Sir, I know inductive reactance, I know capacitive reactance. How to write the reactance of this circuit? So beta, when a circuit has got both inductor as well as capacitor, you say that the reactance of the circuit is nothing but mod of XL minus XC. So first of all, let's find out XL and XC for this circuit. You will say that XL equals to omega L. Here we have a source of frequency 50 Hz. So if the frequency is 50 Hz, you will say that omega is 2 pi f. So 2 pi into 50, that is 100 pi. So XL equals to 2 pi f into L. So that becomes 2 pi into 50 into the inductance, which is 2 by pi. Now you can see that this pi get cancelled. So you get 50 into 2 into 2. That becomes 50 into 4. That comes out to be 200 ohm. The capacitive reactance XC comes out to be 1 by omega C. Omega can be written as 2 pi f. So you get 1 by 2 pi fc. In place of frequency, substitute 50. In place of capacitance, substitute 100 pi microfarad. So 100 pi into 10 to the power of minus 6. So you will say that XC comes out to be 1 by 2 pi f. This is omega. And 100 by pi into 10 to the power of minus 6. This is your capacitance. Now, on solving this, you will see that pi get cancelled. This 50 into 2 becomes 100. There is one more 100, and this 10 to the power of minus 6 goes to the numerator, becomes 10 to the power of 6. So you get 10 to the power of 6 divided by 100 divided by 100. That is 10 to the power of 6 divided by 10 to the power of 4. That is 100 ohm. Now what is the reactance of the circuit? So you will say that for a series LCR circuit, the reactance is nothing but mod of XL minus XC. Here we can say that XL is greater than XC. So the reactance of the circuit will be nothing but mod of XL minus XC, that will be 200 minus 100, that will be 100 ohm. Now bachcho, since we know that XL is greater than XC, this circuit will be called inductive circuit. Why? Because in such a circuit where XL is greater than XC, the phase of potential will lead and current will lag. Such a circuit is called inductive circuit. If for the same circuit XC would have came out to be more than XL, then we would have called the same circuit as capacitive circuit. Now the next question I'm going to discuss is the part of the same question, so keep these results in mind. So the next question goes like, in the circuit shown in the figure, same circuit, the impedance of the circuit and what is the current flowing in the circuit. So you will say that, sir, the impedance of the circuit is nothing but under root of R square plus XL minus XC whole square. We have already found that XL is 200, XC comes out to be 100 and R is given as 100. So finding out impedance is not rocket science. So you will say that the impedance of the circuit Z, which is equals to under root of R square plus reactance square, and we have found that reactance is 200 minus 100, that is 100. So you get under root of 100 square plus 100 square. So that becomes 100 root 2 ohm. Next, the current in the circuit. If they just mention the current, they mean which current? RMS or peak? It means RMS. The RMS potential is 200. So I can say that IRMS equals to VRMS by Z. VRMS is 200. The impedance of the circuit is 100 root 2. So IRMS has to be 200 by 100 root 2. And when you do 200 by 100 root 2, here you cancel it out, you get 2 by root 2, which is root 2 ampere. So for the same circuit, question is, in the circuit shown in figure, find the reading of ideal AC voltmeters. You have got AC voltmeters and you have got DC voltmeters. The AC voltmeters, the AC ammeters are based on something called hot wire instrument. And do understand that you can't use your normal moving coil galvanometer to measure an AC. Why? Because, sir, in the AC, the direction of current keeps on flipping, flopping. So if you use the normal moving coil galvanometer, the needle will keep on flipping, flopping. And the frequency is of the type of 50 Hertz. So it can't flip flop 50 times. So it shows no reading. It is a dead beat. So as to measure AC, we use different type of galvanometers. Such galvanometers are called hot wire instruments. They measure the current flowing in the circuit on the basis of the heat dissipated through the hot wire instrument, and that depends upon the value of IRMS. Hence, hot wire instruments measure IRMS and VRMS. So here we are learning a concept through this question, that so as to measure alternating currents, we can't use moving coil galvanometers, because in AC the direction of current keeps on swapping. So if you connect it to a moving coil galvanometer, the needle will keep on going here and there. How many times? 50 times a second. That's impossible to go 50 times per second here and there. So the needle doesn't move at all due to inertia. So you can't take the reading of AC current using a moving coil galvanometer. What we use is called the hot wire instruments. And remember that they measure RMS value. So question is, find the reading of all the voltmeter. You have to tell the reading of V1, V2, V3, V4 and V5, every one of them. So let's start with the first one. V1 will measure the RMS potential drop across the inductor. And you will say that what V1 will measure is nothing but IRMS into XL, because IRMS into XL will give you the RMS potential drop across the inductor. We have already calculated that IRMS for this circuit is root 2. And we have already calculated that XL came out to be 200 ohm. So you get 200 into root 2. That is your answer. What is the reading of the second voltmeter, RMS value? So we have calculated that RMS current is root 2. The resistance here is 100 ohm. So what V2 will measure is IRMS into R, that is the RMS potential drop across this resistor. So R is given as 100, IRMS is root 2, so you again get 100 root 2. What will be the reading of V3? V3 will measure the RMS potential drop across the capacitor. And the RMS potential drop across the capacitor will be nothing but IRMS into XC. We have calculated XC to be 100 ohm and IRMS came out to be root 2. So you get it to be equals to 100 root 2 volt. Next is we need to measure V4. V4 is connected between inductor and resistance. So what V4 will measure is IRMS into under root of XL square plus R square. So what you get from V4 is IRMS into under root of R square plus XL square. Think of this much part as a series LR circuit. There is no capacitor. So you will say that V4 equals to IRMS into under root of R square plus XL square. We know that R is 100. XL came out to be 200. So when you find this value, this comes out to be under root of 100 square plus 200 square. Take the 100 common outside. So you get 100 times under root of 1 square plus 2 square, that is root 5. IRMS is root 2. So you get root 2 times 100 root 5. Gives you 100 root 10 volt. The next part. What will be V5? The potential drop across this fifth resistance. This will be nothing but IRMS into Z. Why? Because it's connected across the entire combination of LCR. And the impedance of this circuit came out to be equals to 100 root 2. So you will simply get root 2 times 100 root 2, that is 200 volt. And you must notice that what you got across V5 is the same as the potential drop across the source, which also happens to be the potential drop across the source. So that's all in this hour of alternating current. Do practice more questions based on alternating current. See you guys in the next hour where we will talk about electromagnetic waves. Bye bye. So that's all for now. See you guys in the next hour.